All right, so I'm going to give some characterizations of some properties of cofibrations. Um, so uh, of cofibrations. The first thing I want to do is I want to prove that they're closed. Okay, so the first thing I want to do. So lemma. So if f from a to x is a cofibration, then a is isomorphic to f of a, and f of a is a closed subset is a closed subspace of x. All right, so here's the proof. So in order to prove this, we need a lemma. So this, maybe I should have called this a theorem or something, but this will in turn need a lemma. So the lemma we'll do is the following. Okay, so let A and B be topological spaces. Be Hausdorff, and this is important that they're Hausdorff. So one characterization of a Hausdorff topological space is that the diagonal is closed. And so we're going to be using a property like that. Okay? So let these be Hausdorff topological spaces. Okay? So if, so let f, so let f from A to B be continuous. So with a retraction, with a left inverse. Okay, so R from B to A, i.e., we have that R of f of A is equal to A. So this is for all A and A. Okay, then A is isomorphic to f of A and is a closed subspace of B. So this is after identification of A with its image. Okay, so it's saying that if you have a left inverse, then you're going to get this. You're going to get this isomorphism, and then this allows you to identify A as a subspace of B. Okay, so the proof is pretty easy. If you make it easy. So if you make it hard on yourself, these things get really hard. Okay, so since the map has a left inverse, it's injective, right? Is injective. And then hence bijective onto its image. Right, so you just kind of like cancel, right? If f of A is equal to f of B, you apply R to both sides, and then that'll cancel things. Okay, and so now we're going to use that. Okay, so now we're going to use that. So we're going to have a bijective continuous map from A onto its image, and then use that. So this proves so. So this gives. So we get a bijective continuous map from A onto its image and since we are in a Hausdorff situation, our Hausdorff, this is a homeomorphism. Okay, and then we're going to use this Hausdorff condition yet again. So one thing we do is to show that bijectivity of continuous maps means homeomorphisms for Hausdorff spaces, but we'll use it again to get closeness. So consider the set here C so this is the set of B and B such that f of R of B is equal to B. So this is Hausdorff. Oh, sorry, is closed by the Hausdorff condition. So this is the same reason why, if you haven't seen this before, that the diagonal map of how is closed in Hausdorff topological spaces. Okay. Okay, so that gives us that this is closed, and so okay. So this is a set of B and B such that f of R f of R of B is equal to B. So clearly, so we get, so what do we have? We get that C is a subspace of f of A. Right? And then f of A so this is what we need. Okay, so we get f of A is a subspace of B, so that if so let's check this. So this one we get, and then so this one we need to check. So if so consider so what we need is, so if we take f of A as an element of A, of f of A, then what do we get? Well, we need to show that f of R of B is equal to B. Okay, so we do f of R of B of this thing. Okay, and so this is equal to, well, this thing's just the identity, right? So this just becomes f of A. So this tells us that that f of A is an element of C, which proves that f of A is a subset of C. Okay, and that concludes the proof. Okay, so we have the two subsets are contained in each other, so they must be equal. And so since this one is closed, the whole thing is closed. All right. So so now we can apply this lemma to show that the application to that cofibrations are closed. Are closed. All right, so let's let A, okay, to so sometimes we write it like this. This is a fancy arrow for a cofibration. So we'll write this as F, so be a cofibration. Okay, so we'll get two maps, and so okay, so we're gonna use the mapping cylinder here. Okay, so so there's two maps that I want to describe. So one is that the mapping cylinder. Okay, so here, so this is a subspace. So we have this thing, the mapping cylinder. Okay, so let's do this one. The mapping cylinder here. This goes into X cross I, right? So let me remind you again, let's just do the doodle for the mapping cylinder. So here is A, right? And then we do A cross I. Okay, and then this goes into X somehow. Okay, so this is A, this is X, right? And then at 1, this gets identified. So this is like an A cross I. And so this whole thing is the mapping cylinder. And now since so we'll show that it's a subspace, but a priori this could be some complicated thing here. Okay? So in order to define a map to the mapping cylinder, right? We have so we need to say what happens to points here. So these are points like A, T. And then we need to say what happens to points here. So so here we have AT. This will map to f of AT. And then we could just have a point x here. And this will map to x1. And so this is well defined on the quotient. So this is kind of a freebie map. So this is a freebie. Meaning that it works for any map f. It doesn't need to be a cofibration, right? So this is our first. This is a first map that we have. Okay. Then we can construct another map, right? So we'll get another map which is induced by the homotopy extension property. Okay. So we'll get another map here, and I'm going to call it H tilde. All right. And so this is from X cross I. So we're going to have. So what we're doing is we're setting it up so it's exactly like in this situation here. So we're going to end up proving that this is a closed subspace. Okay. So okay. So what we're going to do is we get this thing, and this is induced by. So this map here too is induced by. This thing's induced by the homotopy extension property. And so let me kind of just write out what the homotopy extension property is. So we have A cross 0. And then we have X cross 0. We have A. So this is another way of writing the homotopy extension property. And I think you should check that this is the same thing. So what we'll have is we have our mapping cylinder here. And so we have this top map, right? This just includes into the top of the mapping cylinder, so it's like this one. And then we have this bottom map here. Okay, so that goes into the bottom of the mapping cylinder. These diagrams commute, so this is the inclusion at the 0 point. This one is the map f cross 0. This is the map f cross the interval, so functorially induced. This one is the inclusion at 0, so both of these are the inclusion at 0. All right? This one is the homotopy that we start with, and we'll just, so there's kind of two ways to view this map H. You can just view it as, the cylinder being included inside here, or you can view it as a family of A's, right, parametrized as you go down, right? So there's, a bunch of different maps from A into the different slices, or just the inclusion of this big block. The two ways are, they're equivalent ways of thinking about this. And you should get used to thinking about both ways. All right. So then there's this map here, which is the inclusion at the bottom. So we can call this H0 tilde, right? So this is the inclusion into the bottom part here. So X goes into this bottom slice. And then by the homotopy extension property, right, once you have the bottom piece of a homotopy and a seed part, then you get this extension, okay? So then we get this the second map from the homotopy extension property. Okay, so when we put these two maps together, so we have one map, we have two maps, we'll get into our hypotheses of the theorem. Okay, so we have this map here. This goes to MF. So we had our original map, we called this phi. We called this H tilde. And if we compose these two things, we claim that we get the identity. Note that here we have h tilde of f of a of t, right? So this is just at. And we have h tilde of x0 is equal to 0. And so these things follow from this commutative diagram. So from the way that this is set up here. All right. All right. And so by the lemma, right? So we get that phi is a closed immersion. Closed embedding, right? It means that, okay, and then, so it's isomorphic onto its image, and its image is a closed subset, and that tells us that F is a closed immersion. Okay, and so this gives us the proof of the original statement that we wanted to say. So that gives us that any cofibration. So, and we applied the cofibration hypothesis here, right, using the homotopy extension property. So we get that this is a closed immersion as well. Okay, so that proves that they are closed. All right, so maybe I'll pause here, and then I will add a bit about some more about characterizations of cofibrations.